And so we're going to be starting in on section 4.1, which is specifically looking at this idea of one-to-one functions. Okay, so before that, I want to sort of give you a primer on what these things even are. Okay, so the parent for all exponential functions usually takes the form f of x or y is equal to some number, I'm going to put b, raised to the x power. Okay, now the reason why I chose to use b as the sort of variable here is because b is what we're going to call the base. This is an exponential function, so it's really closely related to exponents. So we're going to have to remember our rules for exponents when we work with exponential functions. And it turns out that a concrete example of this would be something like exponential growth where something doubles in size. Let's say a population of bacteria doubles in size each day. Okay. So for a function like that, we might have 2 to the x, where the input values are represented here by what we're inputting to the exponent, but the base will change, right? So there's a whole family of functions, each which have a different base. So we could have a function where we have 2 to the x. That would be its own parent function. We could have f of x is equal to 3 to the x power, or 4 to the x power, or 5 to the x power. It really doesn't matter. The base could be any number. It could be a whole number. It could be a negative number. It could be a fraction. And so we'll have to figure out what these graphs sort of look like. But in general, exponential functions, I mean, if you've seen the recent graphs of, there's a current outbreak of COVID-19 in India that's actually cause for a lot of alarm. But if you look at like the COVID graph for the United States in the summer of last year, or even in the winter where you have these large spikes in COVID-19, you tend to see a graph that looks sort of like this shape, where it starts off growing sort of slowly, and then at some point it starts growing really quickly, right? So this is the general shape for an exponential function. The parent function tends to cross right here at 1. So this point could be located at 0, 1. That's going to be sort of our reference point for exponential functions. And again, we're going to be contrasting that at some point with logarithmic functions. Logarithmic functions look really strange. Okay, so you're just going to write this down right now, and when we get to logarithmic functions and what a logarithm is, it'll make a little bit more sense. But a logarithm is usually written like this. The word log, so that's log, and then there's a little symbol here, like a subscript b, which is going to be the base of the logarithm. And they don't always do this, but I'm going to. They put parentheses here and then the input for the function. Okay. Again, we're just writing this down. It's a very new thing, very new notation, and we'll talk about it when we get there. We're really going to focus on exponentials, but I just want to give you this preview. An example of a logarithmic function. Well, you might have seen these symbols on your calculator, right? You might have seen log or ln. It turns out that these are logarithmic functions. So like if I wanted to take the log of 2, for instance, right? That's basically a function called the log, and then the input is 2, and it'll spit out some value here. And we don't know exactly what it's doing, but for some reason it's telling us that the log of log 2 is 0.30, blah, blah, blah. These numbers tend to be really ugly, but it's a function that takes an input and then spits out a value, okay? So you could have a function that looks like this. The log or the family of log functions all differ in their base. So we could have log base 2 here of x, or we could have a function that's log base 3 of x. And the really interesting thing about logarithms and why we talk about them in relation to exponential functions, it's because these are functional inverses. So if they have the same base, the exponential function of base 2 is the inverse of the logarithmic function of base 2. And inverse, as we've used it this entire semester, that word just means that they cancel out. So for instance, if I were to, in my calculator, this log button that doesn't have a little base right here is understood base 10. So let me go ahead and say there's a math function in here. If I scroll down far enough, I can use log base, which allows me to change this number to a 2. So that would be log base 2. And I could put a number in here. Let's go ahead and use the number, I don't know, 3. Okay, so the input is 3 there. Well, if I do 3 and I raise it to the exponent, sorry, if I use the same base, 2, so that's a logarithm of 2, and this is a base of 2. So if I raise this answer to this exponent, I should get back to about 3. Now the calculator has a little bit of rounding error, but we're just going to call that about 3. And that's what I mean by if we take the log of something and then we take that output and then feed it to the other function, it cancels out the original function. So we end up what we started with. Okay, that concept is going to make a little bit more sense later on. But it's the same thing as like if I were to take, let's say 5 squared. Let's take the square root of 5 to the second power, right? And in the past, we said that the square root and the square cancel each other out. So if they cancel each other out, we should just end up with 5, right? Because the square root and the square function are opposites, or they're inverses. So if I were to take 2 raised to, so that's the base 2, raised to log base 2, which would be its inverse of some number, let's say 5, then here the exponent, because it's a log base 2 and the base is 2, the base and the log base will cancel each other out and we should just end up with 5. So that's really interesting and actually really useful. So if the bases match here, so this is base 3 and log base 3, then they will cancel each other out and you'll just be left with whatever the input is. Okay. But again, right now that doesn't have to make a whole lot of sense. It's just a preview of an idea that we're going to use later on. And here we'll notice that our function, the graph for logarithms, looks something like this. Where now our reference point right here is at the location 1, 0. And that's pretty interesting, actually, because it looks like these two graphs, if we were to put them on the same graph space, they're sort of like reflections across some imaginary diagonal line. Another thing that's interesting to note is that the reference point for this exponential function is at 0, 1, and the reference point for the logarithmic or the inverse function is at 1, 0. So it's as though the coordinates here have been swapped, right? 0, 1 gets flipped around to 1, 0. Okay. So hopefully, as we get into it and start talking about one-to-one functions, this will make a little bit more sense why you end up getting this as the graph that's the inverse to this. Okay. All right. So it turns out that what is a one-to-one function? That's probably the question we first have to answer. What is a one-to-one function? Well, it turns out that a one-to-one function is a function where the input has exactly one unique output value. Output value. And the important thing to differentiate this from just any ordinary function is that the output is unique. That is, if that y value, it already belongs to a particular x value, then it cannot belong to another x value. So when we were studying functions, we could have a function like, let's say that we have this function, f of x, and I'm going to use a bubble map to describe this. And maybe we had a, b, c, d here, and that's our domain or input space. And then in the output space, maybe we had 1, 2, 3, 4, and that was our range, our output space. So if we had a function where something like this happened, we had maybe a maps to 1, maybe b maps to 2, maybe c maps to 3, and maybe d also mapped to 3. We said that this is still a function because every input value has exactly one output value. But we would say that this is not one-to-one because C and D share the same output. So in other words, the output 3 is not unique. So if we were to look at a particular graph, that's a really good illustration of this. Let's think of the function x squared for a moment. So I'm going to graph the function x squared, which we've graphed before. It's just our parent of all the quadratics, the mother of all quadratics. That graph, if we look at it, well, we could make a table if we wanted to. X squared, and I always like to choose some negative values, so like -2, -1, 0, 1, and 2. And we'll just plug those into the equation and get the corresponding output values, and then plot the output values. So this will be 4, 1, 0, 1, and 4. And so now that we have an xy pair, or a set of xy pairs, we can go ahead and graph this. So we have 0, 0 here. This is -1, this is 1. And those map to 1. So we have this here. Then let's say that this is -2 and this is +2. And let's just say that up here we have 4 right here and right here. So we end up getting this parabola shape that we've now sort of familiarized ourselves with. Not perfect, but few things in this world are. So if I look at this function, if I look at its graph, if I look at its ordered pairs, can anybody tell me whether this function is one-to-one? For every input value that we have, do we have a unique output for it? Or are some of the output values shared?
Some are shared.
Some are shared, right? Like which output values are shared?
4 and 1.
4 and 1, right? Because we have this situation where -2 has an output of 4, but also 2 has an output of 4, right? -1 has an output of 1, but also 1 has an output of 1. So if we were to draw a bubble map of that, for instance, we would maybe write all of our values in the domain. Well, all the values that we've listed here that are part of the domain. It's not the entire domain. We could have -2, -1, 0, 1, and 2. But then our bubble map for our range for this limited set of values are just 1, 0, and 4. And we have this situation where this and this map to 4. So right away, we can tell that this is not one-to-one. Because literally, it means that for 1x, you only have 1y, and they're linked to each other, and that's it. Right? So it's strict monogamy between the input and the output values. Okay. So there's a visual test that we can use to determine whether a graph, if we're not given the equation, or maybe we're given the equation and we're not sure if it's one-to-one, we might look at the graph of the function and then try to assess whether it's one-to-one or not. Okay, so we're going to introduce how do we tell if a graph is one-to-one. So if we're given the graph and we want to answer this question, how do we tell if a graph is one-to-one? We're going to introduce something called a horizontal line test. Now in the past, we introduced the vertical line test to determine whether a graph was a function or not. And now this graph that we see here passes the vertical line test because every vertical line that we draw only has a single intersecting point. But the horizontal line test will tell us if the graph is one-to-one, because it's a way of telling that whether or not our inputs have only a single output, or whether the output has 2 inputs. Okay, so what I mean by that, let me draw a cleaner graph here. Let's look at examples. So 1, we might want to look at our favorite of all the quadratic functions, which is just, well, really any quadratic function, but the mother of quadratics will work. We were just looking at this one. The horizontal line test says that if I can draw a horizontal line through my graph like so, and if that line crosses at 2 places, well then this, even though it looks like a face, this output, or this y value, whatever that y value is, seems to have two x values. So both these x values have the same y value. So the horizontal line test tells us that this function, whatever it is not 1, 2, 1. So let me give you another graph. And maybe it looks like this. Can anybody tell me what kind of function this is? Just by looking at it, its shape.
A cube?
Yeah, this looks like a cubic function to me. That was just, brownie points if you knew that. You didn't have to know that off the top of your head. But being able to identify these things as saying like, oh, that looks sort of cubic, it just becomes helpful for you later on. So if you look at this function, we're just trying to ask that same question. Is this function 1-to-1? Just by looking at its graph. Does anybody know?
I would say no.
Yeah, exactly. And so if we were to draw some horizontal lines, I mean, if you drew a horizontal line right here, you might be misled to thinking that it is 1-to-1 because there's only one intersection here. But you have to be able to do that at all locations on the graph. So as soon as I drew a horizontal line right through here, we can see that whatever this output value, whatever this y value is that's right here, it seems to have 1, 2, 3 outputs. So since we have 3 intersections at a horizontal line, then it can't be one of these special functions that we're calling 1-to-1. So I'll just say that this is not 1, 2, 1. Okay, so let's look at a couple more. Is this function 1-to-1?
Yes.
Yeah. If I draw a horizontal line anywhere on this graph, I'm only intersecting at one location. One intersection. So this is 1-to-1. finally. What about this graph?
One to one.
Yeah. Again, just throw some horizontal lines on there. Or you could throw your pen or pencil horizontally, and we'll see that for every output, so whatever this output is, let's just call it y, it has a unique input. Same thing for this y value, it has a unique input as well. So let me maybe put y1, x1, y2, x2, and so on. So yeah, that's one-to-one. And the reason why we need to be able to tell whether a function is one-to-one or not is because this condition must be met in order for any function to have an inverse. Okay. So let me talk about what inverse functions are. Two functions, and let me just go ahead and give them names, right? F of x and some other function that we might call g of x are inverses if they meet the following conditions. So the first condition is that if f composed with g of x is equal to x, so let me give you an example. I'm going to let f of x equal to 2x. So 2x is this function, right? Where whatever the input value is, whatever x is, I'm going to multiply it by 2. Can anybody tell me or sort of think about what is the opposite of multiplying something by 2?
Dividing by 2.
Dividing by 2.
Dividing by 2. That's correct. So let's say that we have another function, g of x, where we're going to take the input and divide it by 2. So now I have two functions. F of x is this doubling function, and you can sort of think of g of x as being the halving function. That is, it takes the input and divides it by 2. If I were to compose these functions together, right, and remember this open circle means compose. What that means is that I need to take g of x and plug it as an input for f of x. So that's like taking g of x, which is x over 2, and using that as the input for f of x. So if I were going to plug this into f of x, so take this guy here and plug it in for x, well, then I would have 2 times this guy. But if I were to simplify this further, 2 divided by 2 would cancel out, right? And I would just be left with x. So in this sense, the functions f of x and g of x, when they're both applied to some input, they cancel out. And you're just left with whatever that input was. So for instance, let's say I had this input. And let's use an actual number, right? Let me use like 3. And I'm going to throw it into the machine that we're going to call f of x, right? Well, if I do that, knowing that f of x is this doubling function, 3 times 2 is 6, right? So that's the output of f of x. But if I take that output now and I use it as the input of my function g of x, which is the halving function, well, 6, if I plug that into g of x, which is 6 divided by 2, then I would just end up with 3. So that's my final output. But it's as though I started out where I began, right? It's as though I didn't apply any functions at all, because both of those functions are inverses and they cancel each other out. Okay, so that's one condition that tells you whether or not you're dealing with an inverse or a set of inverse functions, functions that are inverses to each other, okay? And that's always how it's going to be talked about. We can only talk about inverse functions. We have to have 2 functions that cancel each other out, right? Then in relation to each other, they're inverses. They're opposites, okay? If we're given 2 functions and they meet this other condition, then we can tell that they're inverses. So 2. Let's say if x, y is an ordered pair from the function f of x, then the ordered pair yx must be, let's say, unordered pair. From its inverse, g of x. So let me give you a concrete example of this. Because basically what this roundabout definition is saying is that if we're given a set of ordered pairs from one function, that we can construct its inverse by simply swapping the position of the first and second coordinates. And that will give us the ordered pair for the inverse function. So let's say that this is my function f of x, like so. Here's my x value. Here's my y value. And I'm just going to come up with a set of numbers, right? And these are just going to be a random set of numbers. Usually I like to start my x values with -2, -1, 0, 2, and 1, right? But I'm just going to randomly select some values for y. So let's say that this is 3, 7, 9. I'm going to go with 18. I'm going to go with 42 for some reason. Okay. There's no rhyme or reason for why I chose those to be the output values for this function. But it does satisfy the definition of being a function because every input has exactly one output. Okay. So if I wanted to construct the inverse, so g of x, let's say that g of x is the inverse of our function f of x, then it would have a set of ordered pairs that we're going to still call x and y. But instead, I'm going to write down the y values as the x values. So 3, 7, 9, 18, and 42. Those would be the inputs. And it would send me back to the output space, or send me back to these x values. So I'm just flipping the order here. So if this is 3 and that's -2, the -2 has to be over here. If this is 7 and -1, that needs to be over here. This will be 0, this will be 2, and this will be 1. So again, the x and y coordinates are swapped. And that's how you can tell by looking at a set of ordered pairs that those two functions are inverses. So to test our knowledge of this, now that I've told you this, I'm going to give you a problem. What I need you to be able to do is decide whether these two functions are inverses. So I'm going to give you the function f, and it's equal to a set of ordered pairs. I'm going with -2, -4, 1 and 4, 4 and -2, 8 and 11. Okay, so those are the ordered pairs in the function that I'm calling f. And then g is the set of ordered pairs. -4, -2, 4, 1, -2, 4, 11, 8. Are these two functions, f and g, are they inverses?
Yes.
Yeah. Yeah, because if we look at these ordered pairs, I've merely flipped the order of them, right? Whatever's an x value here is a y value here. And then similarly, the y values for the original function f, or we can think of it as the original function, has been switched to the x position. Okay. So now I think that this is going to be the fun part. This is really the third condition for inverses, is that the graphs of inverse functions are symmetric across the diagonal line y equals x. Okay, and we're going to see this one put into action right now because we're about to graph some functions and then have to come up with their inverse functions and then graph them on the same axis or set of axes. So what you'll see is that if we can draw this line y equals x, which if you were to graph it, it would be a perfectly diagonal line here. That in order for us to have inverse functions, so I'm just going to draw a function here. There's my function. Let me call that f. The inverse function for it will look like a mirror image across that diagonal line. So let's start with something simple. Let's start with the halving function. So let me write some instructions down. Okay. For the function, and it's a one-to-one function. So we're just dealing with one-to-one functions now. One-to-one functions. We need to graph f, and this is weird notation, f negative 1. This notation where we have a function to the negative 1 power, for whatever reason, mathematicians have decided that this means inverse function. So this is f. You might call it f of x because it takes the inputs x. And then you might call this f inverse x. That's how you would read it. Okay. So we need to find the graph f and then graph its inverse on the same axis or set of axes. So we're going to be given a function. I'm going to start us off with f is equal to 2x, which is the doubling function. And we need to graph this function. Okay, so I think that the exercise is going to be important to do by hand so that we get that down mechanically and hopefully build those connections on what's actually going on our graph space. And then we'll think about how do we construct the inverse function, right? We saw this example before, and we sort of used common sense in a way to find the inverse function already, right? But we need a more systematic way that we can go about constructing the inverse function when we're just given one function. So can anybody tell me what is the process that we usually go through to graph a function? if you were to graph this by hand, what is the first thing that you would do?
Find the value of X. Maybe, I really don't know.
Well, like I need to get ordered pairs so I can plot them, right? So I can just choose whatever I want for X. Okay, so I'm just gonna make myself a table. And I know that the y values are gonna be determined by this function 2x, by the equation. So, why don't we just go ahead and pick some numbers for X? Usually I pick them, but I want you guys to give me a negative number to throw in here. And it can be small and reasonable. You don't have to go crazy.
-3.
-3. Okay, that's good. I like to go with 0. Somebody want to give me a positive number to throw in here?
5.
Yeah. Okay. And that'll be sufficient because I know that this is a linear function. So in reality, I just needed two inputs to get the entire graph. So if I throw -3 into the doubling function, we should get as an output -6. Are you guys okay with that? And if I double 0, or do 2 times 0 here, I'd also get 0. And then if I throw 5 into the function, what should the function spit out?
10.
10. Yeah. I know I've used a lot of scary language up to this point, but I'm hoping that this part isn't so scary. Okay. Now that we have ordered pairs, we can go ahead and plot the x and the y pairs. So we could have, maybe I'll count by 2s because my outputs are sort of big. So I'll go 2, 4, 6, and this is in the negative direction. I'll go 2, 4, and 6 in the positive direction. 2, 4, 6, 8, and I need a 10. So thank you, whoever gave me 5. Just kidding. I do appreciate that you gave me 5. -2, -4, -6. I don't think I have to go down this low. -8. Okay. And I can plot these. So -3, -6 would be -3 is a little bit further out. So like in the middle between -4 and -2. And then -6 would be down here. So I could say, let me put a little half tick mark there, go down to -6. And then that's the location of that point. 0, 0 would be right at the origin. And 5, 10 would be right here's 5. And then we could go all the way up to 10. And that's the location of 5, 10. And since this is the function f, I like to color code these so that we can see 2 different colors on the graph. And I'm going to try to get as straight a line as I can get here. Because when you're graphing inverses on the same plot, it's really important that, we try to make our lines as straight as possible. So it looks like I got a gift card here. I just use this Lowe's gift card as my straight edge. Not super great because of my axes aren't super straight, but we're going to do the best we can do. Definitely want to go through the origin. And there we go. Not the best, but good enough for government work. Something like that. Okay. Now, if I wanted to construct the inverse function, f inverse x, it might be difficult to come up with the equation for that function. But we don't need the equation in order to graph this, because we can come up with a set of xy pairs that belong to our inverse function. So I'm going to put, this is our inverse function. So can anybody tell me what is one of the ordered pairs that belongs to the inverse function?
-6, -3.
Yeah, -6, -3. What's another one?
0, 0.
0, 0. Yeah, that one's not too exciting because if we swap this one, we still end up with the same point. So, but what is the last point that we could have for this inverse function?
10, 5.
10, 5. Good. And so we could keep generating points for our inverse function just knowing that the inverse function has those x and y pairs swapped. So now let me plot these on the same graph, on the same space. Okay. So I'd have to go -3 in the x direction. I'm sorry, -6. And then I'd have to go down to -3. So that would be like right here, that location. 0, 0 is still going to be in the middle. And then 10, 5 would be, Lord, I did not give myself enough. So that's 8. I'm going to go over here, call this one 10. And then 5 would be up here between 4 and 6. So about there. So 1, 2, 3 points that belong to the inverse function. And I'll go ahead and color code my inverse function. Even though I don't have an equation for it, I'm going to color code this as pink just so we have a different color to distinguish it. And I'll go ahead and connect these these 3 points with the straight line like so. As straight as I can get it. Okay. Notice that these two functions, if I were to put like an imaginary diagonal line right through them, they're sort of a mirror image, right? If I just focus on the first quadrant here, it looks like this line, the inverse function, is a mirror image or a reflection across the diagonal line, and it maps right onto the original function, the purple line. The same thing for this thing in the third quadrant. The pink line and the purple line are symmetric across that diagonal. So that's another indication that once we swap the x and the y values, that the graphs of the inverse functions, if they are truly inverses, will end up being symmetric about that diagonal line. Okay. So what I want you guys to do is do this same exercise, but I'm going to give you a different function. I want you to I'm going to give you some inputs, figure out the outputs. I want you to graph the function by hand and then graph on that same plot the inverse function, the way we did here, okay? So this is the function I'm going to give you for now. Here's some examples / practice. I want you to graph f and f inverse on the same axes. And I'll give you this equation. The first function is f of x is equal to x plus 5. And to start you off, I'm going to give you the inputs to throw into this function. I want you to start with -5. And then I want you to go with -1. then I want you to go with 4. And then I want you to go with 11. Yeah, go with those. I'll give you guys about 10 minutes to do this. And then I want you to find F inverse, its X and Y pairs, and then plot those guys. How are we doing on this so far? Anybody have any questions? Were the instructions clear or straightforward enough, or do I need to clarify some things?
No, I think they were pretty clear.
Okay.
Would the inverse equation be x squared minus 5?
What would the inverse equation be? I don't know. I don't think that it would be x squared minus 5. But you're not wrong for thinking that way. That's actually, you know, what just for the other class, just so we're not having a one-on-one conversation here. What she's getting at is that notice that this is a square root function, that we're taking the input and adding 5 to it, and then taking the square root of that. So she's thinking that the inverse function must be a square and must be subtraction, since those are the opposite operations. And that's a perfect line of thinking. But we actually don't have to go that far into it because we're not really looking for the equation right now. And there are some tricky things with quadratic functions where we did see an example where we had a quadratic function that wasn't one-to-one. So technically it shouldn't have an inverse, but there are some things that mathematicians can do to fix that so that we can have a partial quadratic function that could have an inverse. Yeah, and it would probably be something like squaring this and then taking away 5. That's probably close to what the actual inverse would be for this function. But we would probably have to restrict the domain. I don't really want to get into that. Anyhow, let's go ahead and find the outputs for this. Can anybody tell me what the output if we plug -5 into the equation was?
0.
Yeah. What about the output when we plug -1 in?
2.
And when we plug 4 in?
3.
And when we plugged 11 in?
4.
4.
And it seems that I skipped a number. But in any case, I tried to give you guys good input values that would just spit out really nice output values. I probably could have put -4 in there as well, and that would have been fine. But in any case, this will work. Now that we have our set of xy pairs, if we want to get the inverse function, all we have to do is swap those values. So I'll just say that this is 0, 2, 3, and 4 right there. Those will be my x values for the inverse function. And the output values or the y values will just be -5, -1, 4, 11. Sort of just the tedious chore of swapping those xy coordinates. And then there's sort of a tedious chore of actually plotting these things. And I need to go to 11 on the output space. So what do I want to count by? Maybe 2 or 3s. Let's go by 2s. I'll call that 1, 2, 3, 4, 5, 6. So that'd be 2, 4, 6, 8, 10, 12. And I'll try to be consistent over here. 1, 2, 3, 4. But I don't think I had a whole lot of negative output or inputs. So -1 would have to be here. So let me call this -2, -4. And that's good enough for government work because we're just going to -1 and 2. Let me get my output space plotted. And we're not going that high on the output value. So I'll just count by 1s. 1, 2, 3, 4. Those are all positive outputs. These outputs, oh, maybe I should have counted by 2 as well, since these outputs do go to 11. Maybe I'll change this scheme. Sorry, folks. This is why you have to use pencil when you work on math. Okay, so we want to go by 2s. 2, 4, 6, 8, and we don't have to go that high here. I'll do 10, but on the bottom I'll definitely want to go to, nope, I want to go to 11. Go to 12. Then I'll go -2, -4, -6, -8. Okay, now let's see if we can plot these things. So for the first function, I'll go ahead and use purple to plot these guys. And I'll use pink, different color, to plot these guys. Doesn't matter what your color scheme is, but I highly recommend that you use 2 different colors. It's just going to make everything pop. Okay. -5 and 0 will be right here and 0. -1 and 2 will be right here and then up 2. So right here-ish. And now 4 and 3 will be 4 and 3 will be up here between 2 and 3. And 11 and 4 will be 11. And 4 would be, get that dashed line just to guide us, right around there. So as any square root function, when we connect this, it should be connected with sort of a curvy line, like so. So there's the function that we're going to call f. And then we'll take a moment to plot the inverse function points, which are 0 and -5. So 0 and then down 5 would be here. 2 and -1, which would be 2 and -1 would be right around where I wrote the number 2. So I'm going to do that. 3 and 4 would be about here and then up 4. So like right here. 4 and 11 would be here and up here. So got to be careful here. It looks like our line is going here, like so. And that's our function g, or we can call it f inverse, right? F raised to the -1 power. But remember, it's not technically a -1 power. It's read as f inverse. And then you can sort of notice that because we've graphed those on the same plot, that if we were to draw a diagonal line through this, those guys look like mirror images. Okay. So that's how you would go about constructing, if you're given a function, how you would go about constructing its inverse. Okay, so I also want to talk about exponential functions, because that's what we're going to get into here in a bit. So let's graph an exponential function and do the same sort of dance. And I'm going to guide you through this. We're going to graph the exponential function. I'm going to give you the equation. We're going to come up with a set of input values, figure out what the output values are, and then see if we can come up with its inverse function. Okay. So here's an exponential function. Let's go with something simple. F of x is equal to 3 raised to the x power. Okay. So remember a long time ago when we introduced exponential functions or exponents in general, I said that exponents are used to describe or model a lot of different processes in the real world. And I think the example that I used was, it was probably Herbalife or Avon, right? Where if you have some organization that sort of convinces you that in order to get to the top of a rich pyramid scheme, that if you get 3 people to join the business to sell the product, and then they get 3 people, and then they get each of their friends to get 3 people to join the organization, that the growth of the organization should happen exponentially. Where if the scheme is to get 3 people into the organization, well, then that's like an exponent with a base 3. Each time you get 3 more people. So that would be like, if I change the input to 1, that would just be me. I would get 3 to the 1 power, which would be 3. I would have 3 more people in the organization. Okay, not including myself. And now if I went like 1 step out in that process and each of my 3 friends then got 3 people, so not including those 3 people that were original, 3 to the 2nd power, so the second step in that process, they would have 9 people in the organization and so on. And you'll see that the number grows really rapidly. So in common life, we talk about exponential growth as being something that happens really rapidly. But technically it has a particular shape. So let's start off with, I'm going to start with a blank space here. I'm going to start off with the value 0, 1, 2, 3, and 4, just so we can get a feel of this function. And maybe I'm going to throw some negative numbers in here, like -1 and -2. Okay. Now for my example, it sort of breaks down, like my analogy breaks down, because it doesn't make any sense for me to get 0 like people into the organization. Well, if I did that, if I got 0 people into the organization, it would just be me in the organization, right? Like it would just be me selling Avon products out of the trunk of my car. So that makes sense that our input, if we plug 0 into this function, we should get 1, right? And, in the past, maybe it was a little bit confusing that if we raise something to the 0 power, we get 1, but the calculator says it's 1, so we should sort of believe the calculator. And if I throw these inputs into the function, it's the same thing as me saying 3 to what power, right? So 3 to the first power is 3. 3 to the second power is 9. 3, and I'm plugging this in for x. 3 to the third power should be 27. 3 to the fourth power, I have no idea, so we might throw that in the calculator. 3 to the fourth power, 81. Are you guys okay with that? With plugging an input value into the exponent of the function, right? Because that's where the x is. Well, even though it doesn't really, the analogy breaks down and it doesn't really make a whole lot of intuitive sense, we can plug in negative numbers into the exponent, but you'll see what we get here. So if I put 3 raised to the -1 power, let me turn this light off so that you see less glare. You get this number, which if I convert that to a fraction is 1/3. Well, if you remember what your rules are for negative exponents, remember that if we have something raised to the negative exponent, that it flips it to its reciprocal. So 3 raised to the -1 power is 1/3. Does anybody remember what 3 raised to the -2 power is? Well, remember, it's not a negative number. It's this weird decimal. But I don't really like decimals, so let's go ahead and convert that to a fraction. Turns out that it's 1/9. But for our sake, for graphing sake, it'll be okay if we approximate the location of these points. So I'm going to keep this as 0.111 repeating. So let's take a look at what this graph looks like just before we get to plotting its inverse. Let me turn the light back on. Okay. I'm going to leave the scale of my input axis or my x-axis. I'm going to leave it at 1. So 1, 2, 3, 4, and I'll go to -1, -2, -3. And I didn't go that far down into the negative values, but let's go ahead and plot this set first because it's going to be easier to plot. 0 and 1 is going to be 0 and 1 right there. 1 and 3. So maybe I'll just say that this is 3 right here. And you'll notice that my scale for the y, my y-axis, is not going to be a uniform scale. And a lot of times when you have functions like exponential functions, they grow so quickly that it's going to be really difficult to plot the output axis because I have 1, 3, 9, 27, 81. These numbers are just getting big really, really quickly. So I'm just going to say that this is 3, this is 1, this is 3. I'll say that the next one is 9, and I'll put it up here a little bit higher. I'll put my 27 up here a little bit higher. And then obviously 81 has got to be really high up here. But I really don't have room, so I'm just going to say whatever 81 is up there. So y-axis is not to scale. It's not a uniform scale. But now I can just go ahead and sort of plot these things. 0 and 1 is here. 1 and 3 would be here. 2 and 9 would be up here. Ish. 3 and 27. It's like that. 4 and 81. -1 and a third would be like down here. So if I cut this into thirds, it would be like right there. And then -2 gets even smaller than that, but it's not quite 0 yet. So I'm going to get even lower there. And you can imagine that as I go out to more negative inputs, that this line is going to get closer and closer to 0. So you end up getting this really interesting curve that gets really close to 0, but doesn't really touch and should go through these points and then grows really rapidly here. And it should be a straight line, but because my scale is really ugly, it's a little bit lumpy. Okay. Now for the inverse function, I'm going to call this f inverse of x. For this exponential function, its inverse, I have no idea what the equation is. I have no idea what to call this equation. But I can find points for the inverse function by just simply swapping my x and my y values. So that's what I'll do. I'll just say, let's go ahead and call this, just going to list these 1/9, 1/3, 1, 3, 9, 7, and I'm just going to run out of space there. So I'll omit this last one. 1/9 maps to -2, then 1/3 to -1, 1 to 0, 3 goes to 1, and then 2, 3, 2, 3. Okay. And if I had not run out of space, I would have gone ahead and included 4 over here and 81. Sorry, did I do that correctly? This was 27. and this is 81. Okay. Just swapping those x and y values. But in any case, let's go ahead and plot some of these. 1/9. Have no idea where that is. Okay. 1/9 is over here, really close to 0 because it's pretty small, 0.111. So that's the x value. Then -2 is my y value. So I'm just going to say that this is -2 down here. 1/3 is going to be a little bit higher than that. And we should be at -1. So like here, 1 and 0 is right there. 3 and 1 is out here. 9 and 2. Well, 9 and 2 would be, let's say this is 5, 6, 7, 8. I'm just going to say 9 is all the way out here. And then 2 would be right here. But notice the difficulties that I'm having with this graph already doing it by hand. Because the scales shift really weird. But you'll notice that the shape that it's making, let me go ahead and color code this. This is going to be in pink. If I sort of start to create this shape, you'll notice that the property of inverses say that we should sort of be symmetric across that diagonal line. And that's about what we get. Okay. So we've constructed a function that's an inverse for our original exponential. And it generates this graph here. Well, it turns out that mathematicians have just defined this function to be a logarithmic function. And logarithms are defined simply as the inverses of exponentials. So whatever this is doing to our input values by taking it and making it the exponent on the base 3, the logarithmic function is going to be reversing that process to give us the output, the original input. So this has to be a logarithmic function for the base 3. And so what mathematicians do is just write this as log 3 of x. They have simply defined the inverse function to be this set of symbols. But in
Professor,
general,
I'm sorry.
no, go ahead and ask.
Can
You
you
got it.
repeat why is a logarithmic function base 3? I didn't catch it. Oh, because the function of, okay, sorry.
Yeah, no, exactly. The reason why we call this the log base 3 function is because it's defined as the inverse of this original function whose base is 3. So in order for logarithms and for exponents to be inverses of each other, they have to be related by the same base.
Yeah, thank you. Yeah.
And you could do this process for any base. Like if we had done a function f of x is equal to 2x, we could come up with some input values, get the output values, swap them, and then we'll call that function log base 2 of x. And it'll generate a function that mirrors across that diagonal line our original exponential function. Okay. And so we're going to be getting into solving eventually exponential functions where, let me just give you a preview of something. So like if I needed to solve the equation 3 raised to the 2x plus 5 power is equal to, let's say 3. And I'll say this is the 3 to the 4x. Okay. Well, the reason why we're introducing exponential functions and logarithmic functions is because here we have, in this equation, the exponents have the variable that we want to solve for. Okay. So somehow we need to cancel out the base 3. But we can't do that by dividing by 3 to the other side, because we're looking to cancel out the base. So what we would want to do to cancel out the base of a function is we would have to keep in mind that if you have a function like 3 to the x power and its inverse, which would be, let's call it g of x is equal to log base 3 of x, then if I take the log base 3 and I wrap that around 3 to the x, then the log base 3 cancels out the exponential base 3. And we can basically get this thing that was originally the exponent, we can free it. So in this particular context, what it will look like, again, just as a preview, you don't have to understand this right now. We're going to get to it. What it would look like is just like we, if we had something added to one side of the function and we wanted to cancel it out or move it to the other side, we would subtract or do the opposite operation. Here we're going to do the opposite function to both sides of the equation. We're going to say, I'm going to take this guy and take the log base 3 of both sides of my equation so that the log base 3 and the exponential base 3 cancel out on both sides. And that will leave me with an equation that is much simpler to solve. Right? Now, this is just a linear equation. I could solve for x in the way that we've been doing this entire time. But this only makes sense if we talk about inverses, inverse functions, so that we can apply some inverse function to both sides of the equation, simplify this, and then you could just, subtract 2x, blah, blah, blah. You get 5 is equal to 2x, and so you get x is equal to 5 over 2, right? But the new part is going to be the hard part. So let's take a 10-minute break. Let's come back at 2:10. And then we'll talk more about how we go about solving exponential equations. Okay, guys. Hopefully that break was a little bit, well, relieving, relaxing. Hopefully you guys were able to get some water, get up, stretch, walk around. Because for this last part of the class, what we're going to be looking at is solving equations. And we're going to need to be able to solve equations that have exponents in them, or that have a variable that are in the way I think about them is that the variable is trapped in the exponent part of the expression. Okay, so maybe I'll write that down. The variable is trapped in the exponent part of the expression. And that's sort of like asking, and I'll start with something a little bit simpler. Like 2 to the x power is equal to 256. And hopefully I've chosen my numbers correctly. Okay, yeah, I have. So if you were trying to solve this question, this equation, you sort of have to think about mathematical statements or equations as a statement, right? What this statement is asking you is essentially 2 is the base, right? So 2 raised to what power produces the output 256? So basically I'm asking, what power do I need here in order to get 256 if I'm taking the number 2 and raising it to some power? And the brute force method of solving something like this would just be to say, well, let's just start guessing. We could guess and check, right? I know that 2 to the 2 to the 2nd power is 4, right? And that's too low. So my exponent here needs to be higher than 2. So I might guess higher, like, let's guess really high, like something, let's go with 8. Well, I just guessed correctly. Let's pretend that we weren't guessing 8. So like, let's guess something small like 2 again. Let's say that we went something higher than 8, like 15. That's too high, right? So then I might guess something lower. I might try something like 2 to the 4th power. 16 is too low. And then you might just, go up by there and say by 5. No, that doesn't work. By 6, that doesn't seem to work either. And then eventually we would get to 8 and see that, okay, well, the missing exponent in this expression or this equation has to be 8. So x is equal to 8 by the brute forcing method. That would be the solution. But I know damn well that you guys don't want to brute force it. You want some method that's going to be able to basically not have to be guessing around, right? Because you can't depend on a guess and check method on the test. So what we need to do here is follow this strategy. And it is a little bit of a guess and check. But what we'll do is we need to take the numbers on each side of the equation and write them in some form where their bases match. So what I mean by that is that if we were looking at 2 to the x power is equal to 256, well, I want to identify what is the base that I'm looking for here. And right now, the base on this exponential is a base 2. So you need to ask yourself, can I write 256 as 2 raised to some power? And for this example, I can write 256 as 2 to the 8th power, right? And we sort of brute forced it in the calculator a little bit. There is a little bit of brute forcing. But what we would do over here is we would rewrite this equation. And I'm going to write 2 to the x power because we're not doing anything there. But what I wanted to do was take this larger number, see if I can rewrite it as 2 raised to some power, and I can. And now if I have this expression here, since I know that 256 and 2 to the 8th power are the same value, I can make that substitution. Well, now if the bases match here, then I don't really care about the bases anymore. I have 2 to some power is equal to 2 to some power. That means that the powers have to be equal to each other. So what I can do is once the bases match, I'll drop the bases, and then I'll set the equation, just an equation where my exponents are equal to each other. But in most of the problems that you'll get, we'll need to use some of our past or previous exponent rules to manipulate these forms so that we can get the bases to match exactly. So what do I mean by that? Let's look at the next example. We have 1/9 raised to the x power is equal to 729. And this is a situation where we definitely don't want to be guessing. You know, we take 1/9 and raise it to some exponent, and we're supposed to get 729. I have no idea what the exponent is supposed to be. But what I want to do is I can ask myself, and this will sort of be like scratch work territory. If I have a base of 9 over here, is there a way for me to write 729 as 9 raised to some power? So we might brute force that or guess and check in the calculator. And we might come to the conclusion that this is equal to 9 raised to what power? Well, I might start with 9 to the second power. It's too low. 9 to the third power, and that's 729. So because these two expressions are equivalent to each other, I can make this substitution where now 729, let me just sub that out for 9 to the third power. We haven't done anything to the other side. We're just substituting out the 729. Does anybody have any questions about that part? Okay. Well, on the last problem that we had, we wanted to match the bases exactly, where we had 2 to the x is equal to 2 to the 8. But the bases matched exactly. On this problem, the bases don't match exactly. I have 1/9 to the x power and 9 to the third power. So I won't be able to cancel these out until I can write this side as 9 raised to a power. So somehow I need to be able to write 1/9 as 9 raised to some power. And does anybody remember what exponent, like if I had 9 raised to some exponent, what exponent would I need so that I could flip that to the reciprocal 1/9? It's been a while since we used our exponent rules. But it turns out that it's -1. So remember, a -1 exponent flips the base to its reciprocal. And that means that really that goes both ways. So if I have 1/9, I could write that as 9 to the -1 power. So I can take this expression here, 1/9, rewrite it as 9 to the -1 power, but I would still have this x as my exponent. So can anybody tell me what happens when you have a power raised to another power? What do I do with these exponents? For instance, if I had 2 to the second power and then I raise that to the third power, what should I get over here? 2 raised to what power? Maybe it's been a while.
The root, therefore, you have the power for 2 power 3 root 2. No, I was backwards.
No. So this is the rule that if I have something raised to a power and then I raise that to another power, you multiply those powers. Right? In the same way that we learned about exponents, that if you have x to some power and you have the same base raised to a different power, that you add those powers. So these are the rules that are gonna come into play for solving exponential equations. So if you're a little bit fuzzy on your exponent rules, you want to break out your notes on exponent rules. So we need to multiply these powers. So we have 9 to the -x power is equal to 9 to the third power. So that these bases now match, which means that their exponents need to be equal to each other. So -x is equal to 3, which implies that x is equal to -3. So we'll want to remember our rules for exponents as we solve some of these problems. And sure enough, if we wanted to check this in the original expression, we could take 1/9, raise it to the -3rd power, and see if we get 729. And that's pretty straightforward to do in the calculator. Let me write this as a fraction. So 1/9 raised to the -3 power is 729. But we have more examples, so you get a feel for the flavor of these kinds of equations. So let's look at this one. Let's solve 4 to the -x is equal to 1/256. And I like to put all my scratch work over here. So when you start a problem like this, or when I start a problem like this, what I think about is I think about the bases that they gave me originally. And I try to see, can I write these as something raised to a power? So I always do like a box raised to another box. And 256 is equal to some box raised to another box. And I try to fill in those boxes by matching the bases here and seeing if we can get something that's similar. So can anybody tell me, can I write 4 as something raised to a power?
Two to the second power?
Yeah, let's try 2 to the second power, right? And if I want to match the base here, then that means I'm looking to change 256 to 2 raised to some power. Does anybody remember from a previous problem what the power here has to be? Two raised to what
8.
power? Yeah, it's 8. Good. So what that tells me is that I can rewrite this expression as 4 is the same thing as 2 raised to the second power. But I'm only replacing the 4. So I still have this negative x power on the outside. And then on the other side of the equation, I have 1 over 256. So I can only replace the 256 part with 2 to the 8th power. And then you want to start piecing together your exponent rules. Okay, so the exponent rules that are going to be helpful for manipulating some of these parts of the equation, on the left-hand side, we need to remember that x raised to a power, and if it's raised to a second power, or a different power, that we multiply those powers. So this would be like 2 to the second power raised to the negative x power. So I can multiply those powers, and I should just get 2 to the negative 2x power. The other rule that's super useful, especially when you have fractions, is that if you have 1 over x, that you can write that as x to the negative 1 power. But more generally, if you have 1 over x to some power, let's say n, then you could rewrite this as x to the negative n power. And we're going to use this rule, which we've already applied. And this rule here would allow me to change this number from 1 over 2 to the 8th power to just 2 to the negative 8th power. So because our bases match, that means that the exponents have to be equal to each other. So I usually say, just like Skrillex or any dubstep, you're just going to drop the bass and set the exponents equal to each other. Well, now we just have a simple linear equation, so I'm just going to divide by 2 on both sides, or but divide by negative 2 on both sides. X should be equal to 4. And then as always, we can go ahead and throw that 4 raised to the negative, and then our solution was 4. So if I put this into the original expression for my exponent, then I should be getting 1 over 256 when I when I throw that into the calculator, obviously the calculator is going to spit it out usually as a decimal. So let's flip that back to a fraction. And yeah, for sure, we get 1 over 256. Okay. So what I'm going to do is give you a problem, and I'm going to step back and give you guys 2 to 3 minutes to try to solve that. So try to solve this one on your own. 4 raised to the 8 minus 2x is equal to 256. This one should work similarly to the last one we just solved. Does anybody have a solution yet? Or is anybody stuck?
I'm stuck.
Yeah, where are you stuck, Kelly?
Okay, I got 2. I thought about the bases. I got 4, so that's 2 to the second power. And then 256 is 2 to the 8th power. So then I rewrote it 2 to the second power in parentheses. And then I have to bring my 8 minus 2x next to it, right?
Yeah,
Equals 2 to the 8th power.
yeah.
And then do I have to get x by itself? So I have to divide by -2 on the top?
I think you might be flying through it a little bit too quickly.
Okay,
Right here, when you have a power raised to a power, what do we do with those powers?
I need to multiply them.
Got to multiply those powers. But in this case, because it's a power raised to a polynomial expression, we have to multiply in the sense that we're going to distribute the 2 to
Okay.
both of those terms. So we should end up with 2. Now it's raised to the 16 minus 4x is
Okay.
equal to 2 raised to the 8th. Was that a little bit tricky for anybody else? Or was there anybody who was able to figure that out?
I did that way, but I wasn't sure if I
Okay.
had, but I did.
Yeah. Yeah, so if you were thinking along those lines, then you were thinking in the correct direction, okay? But don't feel bad if you didn't, right? This is sort of new. But just remember, if you're multiplying a power to a power, and that power happens to be a polynomial expression, then we'll multiply it the way we multiply polynomials, which is through the distributive property. Now that we have the bases match here, well, now that's the fun part, because we can just say, forget about the bases. We're focusing on the exponents. Let's set that up as an equation. 16 minus 4x is equal to 8. And that's just a linear equation. We can solve that by just getting the numbers to one side, getting the x to the other side. So I could subtract 16 from both sides. Negative 4x is equal to, this would be negative 8. Divide by negative 4 on both sides. And x is equal to positive 2. Okay. Well, the last thing that I have to introduce to you guys, because there are some applications or some word problems in this section. And this might be, it may or may not be useful to you in your daily life or in your non-mathematical lives. And that is finance formulas. And finance formulas often use exponential expressions or exponential terms. And so if you go to the bank or you're going to make an investment into an investment account or something like that, and that investment might compound annually or daily or what have you, over time, you're going to be collecting interest, and you expect that if you put money into an investment account or a savings account, that that money will grow at some rate or based on some formula. Well, our compound interest formula that's used quite often is given by this formula. A is equal to P times 1 plus R over N raised to the NT power. And I'll explain what each of these letters means. Okay, but the idea here is that we have this formula that we're going to need to be able to use to solve financial questions. In this formula for compound interest, you might go to the bank and, you know, this investment account might say that your investment is compounded quarterly or biannually or weekly. Okay, so for this kind of formula, you're going to take some sort of principal investment. So P is going to be standing for the principal or the initial investment. I'm just going to put initial amount here. Usually we're talking about money, but this formula turns up in places other than the financial sector. So right now we're just going to be talking about money. P will represent the initial amount. A is going to be the annuity. That's an ITY, but I like to think of it as the future amount. So how much you expect to gain at the end of that investment. R is going to be the interest rate. Usually this is given as a percentage. Like you might have an interest rate for like a mortgage loan of like, let's say 2.5%, so 2.5%. We'll want to express that as a decimal though. So for example, 3% as a decimal would be 0.03. Basically, you're moving the decimal point over twice to the right. The N here is I call it the compounding number, or how often that investment account is compounded per year. And there are some key words that I'll give you here in a second for the compounding number. So if it says compounded annually, then that tells you that N is equal to 1. Semi-annually, 2. Quarterly, and then these become a little bit more natural or common sense, like there are 4 quarters in a year. Monthly, there are 12 months in a year. Weekly, there's 52 weeks in a year. And then daily, there's 365 days in a year. So does that cover all of our variables? No. We still need T. T is time in years. Okay. So as long as we have everything on the right-hand side of the equation, we can find the future amount. So what we'll need to be able to do is read some of these problems, figure out what has been given to us and what we need to find. Okay. So let's do one example problem, and then I'll pick up where we left off. I'll pick up on these financial problems at the beginning of class next week. But let's find the future value. And so we are given that we have $1,972 invested for 12 years at 4% in an investment account that's compounded quarterly. So what you'll do here, and this is my strategy going into all of these problems, is we'll write the formula down. A is equal to P times 1 plus R over N times N to the T power. And then I'll ask myself what has been given to me. So I'll write down what's given. And I'll try to figure out what is it that I need to find. So they said find the future value. That tells me that I need to find what A is. But in this word problem, I know that 1972 is the amount of money that I'm investing into this account. I know that the rate of this account is 4%. So as a decimal, that would be 0.04. It says compounded quarterly. So if you just reference that, that set of key terms, quarterly means that it's compounded 4 times out of the year. And T is equal to 12 years. So what I can do is just plug and chug. That's going to be my strategy here. Plug and chug. And when I say chug, I mean chug like a train. I drink responsibly if you're drinking while doing math, okay? So we have A is equal to, and I'll go ahead and set this up, 1972 times 1 plus 0.04 over 4 raised to the NT would be 4 times 12. So I have everything over here, and once I go ahead and throw that into the calculator or simplify it little by little, I'll be able to figure out what my future value is supposed to be. So I'm just gonna simplify this a little bit at a time. So maybe the first thing I might try to do is simplify this fraction first, and then the exponent here. Well, I know that 4 times 12 is 48. Well, now I'm starting to doubt myself, so I'm going to throw that in the calculator. 4 times 12 is 48. Good. But I don't know what 0.04 divided by 4 is. 0.04 divided by 4. Turns out that that's just 0.01. Well, then I can go ahead and add this stuff together and then raise it to that power. So this is going to be 1.01 raised to the 48th power. I can apply that exponent, and then I'll just save this multiplication for the end. So I should get 1972 times 1.01 raised to the 48th power. And that's 1.61. And I'm going to keep all of the decimal places just so that I don't make a mistake. And I'll round at the very end. So now I'm just going to multiply this number times the 1972. And I should get 3,179. And since we're talking about money, we just want to round to 2 decimal places. So this will be 31 cents. This is the future amount that I can expect after investing $1,972 for 12 years at 4% compounded quarterly. At the end of that 12 years, the account grew to $3,179.31. Okay. There's different flavors of these financial problems. So like I said, we didn't have time to get into the thick of it. I just introduced this formula, but we'll start working on some of these financial problems at the beginning of class next time. So since we're out of time, I will see you guys next time. If you have any questions, if you need help as you're studying and preparing to take test 4, reach out to me. We'll set up something if we need to do a one-on-one session, or drop into my Math World hours tomorrow or Friday. If you need some help on Saturday, feel free to reach out to me too, okay? I want to make sure that you guys do well on the test. So that being said, you guys enjoy the rest of your day and your weekend. and I'll see you next time.
Thank you.
Thank you.
One
you.
question.
Yeah.
Last question.
Yeah, no.
When is going to be the last class, like face to face? When is the last class we're going to have?
Next Wednesday.
Next Wednesday. So, okay.
Mhm.
And then it's the final test.
And then it's the week of finals. Yeah.
Okay.
Good question.
Thank you. Okay. Have a nice day.
You too.